I should have rewritten what you guys put in the paper. I mean, a lot of the technical stuff we don't really need to be dealing with. See, the thing is, most people don't know what instantaneous high-speed infrared interferometers are.
It's true.
You know, so you know, for this audience, what I would do is there we go. There we go. Most people don't care about internal NASA documents. Yeah, that's probably fine. Make it a little bit more generic. Pardon? No, I'm fine for the moment. Theoretically, I should last an hour and a half without a drink. Yeah. Okay. Sure.
I remember him. I liked him when he was here last year. I liked him a lot. I remember his ball.
Me too.
He was very good. I do remember. I do remember him being here.
Do my last minute meeting preparation.
Oh, sure. No.
Yeah.
Do you need to test that or anything? It's muted over here, but
It's one of the things that you always you learn.
I understand. Trust me. I had a guy one time who was a minister Methodist
Yeah,
annual
yeah.
conferences.
He did too.
He didn't, he walked into the bathroom and didn't tell us, and it went, you know, you hear it all over.
Oh, yeah, oh, yeah. It hasn't happened to me, but it's happened to people I know.
Yeah.
Look, we made it.
Yeah, he made it. 3 minutes to go.
Where do you want to go?
Do the one right there on the left. Well, I think we're going.
No, you can wait. He's coming out now. They're coming out now. Go ahead. Hello. He went to the bathroom.
So, Mike, where are you gonna park your van?
Behind Hoover.
Right, like right
Oh, like right in front of the door.
okay, then you're okay.
Why?
A tree that on Central fell or a large limb fell off and fell on two cars that were parking in that area. So our vehicle was over.
So if my van would have been where it was normally, it would have been crashed.
I think so.
So that was, so either the car that's on the grass where I normally park is
Possibly.
either Bobby Horton
I know
or
Sean.
Sean.
Yeah,
It's one of their cars.
it possibly.
So a car caught on fire?
Yeah, I guess a large branch fell off a
Oh.
tree.
So, and I typically park in that spot.
I know.
So that's
And
why
I
all the,
didn't today because
all the
somebody else
sirens
did.
was the branch?
I believe so.
You don't want to do that with the wire because it'll pop and crackle.
Okay,
So, if you want to hide the wire, we can hide the wire, but you just don't, because you don't want to bunch it up because it'll pop.
Oh.
It'll click. Just coil it. Yeah, that works too. Let's fix this. That'll work.
all right.
Okay. Where are you going to be?
By the podium, if you want.
That's good. Yeah, that'd be great.
Okay. Well, feel ready to go?
Yeah.
Good afternoon, everyone.
I'm John Mann. Thank you. I'm John Mann, Director of Education for Lakeside. And for today, we're happy to welcome back Phil Stahl to Orchestra Hall. Phil is a senior optical physicist at NASA Marshall Space Flight Center in Huntsville, Alabama. He is the leading authority in optic systems engineering for many of the world's largest telescopes. And Phil is a recipient of a NASA Distinguished Service Medal, a fellow and past president of the International Society of Optics and Photopics, and a member of the American Astronomy Society. And for this afternoon's session, the Webb Space Telescope, NASA's next large space telescope, which will launch in the early 2040s, is predicted to detect and characterize approximately 25 Earth-like planets, all of which will be around sun-like stars. Phil will explain how planetary systems are created and detected, and share images collected from space telescopes past and present. As a reminder, this evening we're at Hoover Auditorium. Musician and storyteller Shawn of the South and instrumentalist Bobby Horton will be playing. And at the conclusion of this session, and actually any sessions in education, I do ask if you would pick up a feedback form. It does help me when it comes to future programming for future years, and it is appreciated. And I also ask you please mute your cell phone ringers and help me in welcoming Phil Stahl.
Well, thanks, John. So last year I talked, if you saw the talk, last year I talked about 50% on the engineering, the design and manufacture and testing of the Webb telescope, and then some of the science. This year I'm going to talk mostly about the science observations that have been happening over the course of the last 12 months, and then I'll move into a little bit at the end about the next one that we're starting to work on recently that John was mentioning, and then a little video that just came out yesterday. And so as I go through this chronologically, there have been literally a press release every single week of the last year. And so I've taken those press releases, turned them into a PowerPoint page, if you will, and then we can talk about each of the press releases. And I'm going to kind of go through it in chronological order so you get a sense of how the data is coming out of the telescope, with some review as to, bringing everybody to a common point on where the telescope is. So we launched about 2.5 years ago, Christmas Day. It's 6.5 meters, so 6.5 meters is about the size of this room in diameter and height. And the sunshade of the telescope is about the size of a tennis court. And then 2 summers ago, these were the first release images that came out. Very pretty pictures. And so you get an idea where we were 2 years ago. And the purpose of the telescope, and the purpose of the Astrophysics Division, so this telescope is a mission of NASA's Astrophysics Division. And the goals of the division is, how did we get here? How did the universe form and come together? Where are we going? What's going to happen to the universe? And the question a lot of people are interested in is, are we alone? Is there other civilizations or planets with life out there in the universe or in our own galaxy? And the Webb science themes are, we start with the Big Bang, and I'll touch there a little bit. We go through something called first light, and I'll make sure and I've tried this year a little bit harder. I put in some more introductory material to make sure that everybody understands what some of these concepts are. Galaxy formation, evolution, how do stars form, how do planetary systems form, and how do we begin the search for life elsewhere in the universe. So the first question is, what is first light? And actually, what is light? And so light is produced by electrons moving, and if electrons and atoms are just vibrating, heat. So heat is light. So when you go outside in the sunlight and you feel that heat on your hand and back of your head, that is light. Radio waves are light. X-rays are light. Gamma rays are light. These are all things that are electromagnetic radiation. And we only see a very small piece of the electromagnetic spectrum, which we call the visible. And one of the things that's really important to understand is the concept of spectrum, because Webb uses spectrometers. A spectrometer is an instrument that stretches the light out into individual wavelengths. And those wavelengths tell us things about what we're looking at. So a hot object glows, and it just has a continuum. So if you were to take a grating and look at a conventional light bulb, you'd see just a continuum of colors. But if you take a grating and you look at an LED light bulb, you see specific lines. And so hot gases, LED devices, they produce lasers, they produce light with spectra, specific wavelengths of light. And gas, if we take a white light and run it through a cold gas, the gas absorbs at those lines. So looking at emission lines and absorption lines tells us things about our light. And there we go. And so this is something called a black body curve, is that a hot object like our sun is about 5,000 degrees Kelvin, really, really hot, produces light where the peak wavelength is in the green-yellow. Our bodies, we are at about 300 degrees Kelvin. Room temperature is about 300 degrees Kelvin, and we produce light that peaks out at 10 microns. And so that's infrared. And so different objects with different temperatures have different peak colors. And so here's an example of the burner in my cottage. And when it's off, it's black. And as it gets hotter, it starts to glow. And so the redder it gets, basically the hotter it is. So this is a black body object. The color of the object tells you its temperature. I said everything begins with a Big Bang. And so we have the Big Bang, and then we have today. And what we have is, different missions look at different pieces of the life of the universe. The MAP mission and the COBE mission is looking at the microwave background. Hubble looks in the visible, so it looks more close. In Webb, because it's in the infrared, it's going to look further away, and because it's bigger, it's looking further away. So we're studying the entire timeline of the universe. The further away we look, the further back in time we're looking. And so the concept of the Big Bang actually began back in '64 when these guys from ATT Bell Labs discovered noise in the microwave. And they discovered the microwave background left over from the Big Bang. And then in '89, NASA launched the Cosmic Background Explorer, COBE, which found that microwave background is lumpy, which is an interesting question. Why is that lumpy? And John Mather was the co-investigator on this experiment. He got the Nobel Prize in '06, and he was actually the Webb chief scientist. He's now moved on to actually other things he's interested in. So then the other piece of the why we have Webb is Hubble. So in 1995, Hubble looked at a tiny, tiny piece of sky where that little X is by the Big Dipper, where there was nothing. There was nothing there that we could see, and they took data for 10 hours, or for 10 days, 342 exposures. They added them all together, and this is what they got. And it changed everybody's perception, is that the universe is just completely full of stuff that we didn't know about. The universe is bigger and more complicated than ever imagined. And so that then led to this idea of understanding the early universe. Inside of this image, that little red dot in the upper right corner is a galaxy that was existing about 480 million years after the Big Bang, something called a Z10 redshift. And it's discovered using something called the redshift dropout technique, which I'll explain in a couple of charts. But basically, the further away something is, the redder it is. And so when you look at it in the visible, the yellow and the green and the blue, and if it's not there, but it is there in the red, then it means it's really far, something very far away. So this is the reason that we have redshift. We have redshift because the universe is expanding. And as the universe expands, space gets stretched. And so a photon that gets emitted in the blue, by the time it gets to us, has been stretched into the red. This is just sort of another example of if you think, so, and the way to think about the universe is that it's like the surface of a balloon, is that everything in our universe is sitting on top of the surface of the balloon, and as the balloon expands, everything gets further away. And the light is traveling along the surface of the balloon. So it starts out being blue, and then as it gets stretched out along the surface of the balloon, it gets turned into the red. Now, what is important is that when we start looking at spectra, is remember, spectra is related to electrons inside of atoms and those electron transitions, and the electrons absorb light. So the emission lines and the absorption lines tell us interesting things. So our sun has this spectrum across the bottom where each of the elements in our sun has a different absorption line. And that those same absorption lines, as you get further and further and further away, they shift into the red. They get red shifted. And so we can tell how far something is away from us by where those spectral lines get shifted into the red. The reason we want to go to space is that we can't see our own atmosphere in the infrared. So the Webb telescope operates, I don't know if the red dot. So the Webb telescope runs from here in the red all the way out to about 28 here. And so all of these wavelengths here in the middle, our atmosphere blocks. And so by going above the atmosphere, that allows us to see it. Another reason for going in the infrared is this is a very famous image on Hubble called the Pillars of Creation. And this is what it looks like in Webb. And so by going into the infrared, we can see through the dust and see what's going on in the star growing activity. So this is what Webb looks like. Again, it's about the size of this room. The sunshade here is about the size of a tennis court or a pickleball court. And then the spacecraft is on the warm side. It faces the sun, and the telescope is on the cold side. And each one of those sunshades drops the temperature of the telescope by about 50 degrees Kelvin, 50 degrees C, which is about 120 degrees Fahrenheit. And so this telescope is really, really cold. And where it orbits and it goes around the sun with the Earth in an orbit called a Lagrange point number 2. It's about 3 times further away from the Earth than the moon. And it's just rotating around that point there as it goes around the sun. And the reason it's located there is it's sort of like if you do any camping or hiking and you use topographic maps, this is a map of the gravitational potential in space, and it's in a saddle location. So it's a very nice location. It's a very flat location. If it gets too far this way, it'll fall into the Earth. If it gets too far this way, it'll fly out. And so it just, by sitting there, and it doesn't require very much to keep it there. This is another idea of how big it is. Okay, so because it's big, it has a really small focal point. You know, if you ever played with a magnifying lens and burned something with sunlight, a little small magnifying lens produces a bigger spot, and a bigger lens produces a smaller spot. So this is the thing here, is that with Webb being 6.5 meters and really large, it produces a really small spot. But because it's in infrared, its wavelength is longer, the spot that it produces is proportional to the wavelength divided by the diameter. Hubble is in the visible, but it's smaller. So the interesting thing is Hubble at 1.6 microns has a focus spot of 0.14. You don't need to know the units. And Webb at the same about the same wavelength, has a ratio of wavelength to diameter of 0.06. You can see that Webb actually has a better focus, a smaller spot, better, we call it better resolution. And those of us that are getting older and we have a little trouble with our accommodation, you understand when things are slightly out of focus. And you have to take off your glasses to read things sometimes. The other telescope it relates to is Spitzer, was a far infrared telescope. And Spitzer's lambda over d, wavelength over diameter ratio, let's say 24 microns is 6, and Webb's is 0.6. So Webb is 10 times more better resolution than Spitzer. And then this down here at the bottom shows the coverage. Hubble is an ultraviolet divisible, Spitzer was an infrared, and Webb is covering the range in between. And the other thing is you look at its field of view, is that because Spitzer is a small telescope, it has a very large field of view. It takes a wide angle image. If you're a photographer and you got a 28 millimeter lens, you get a wide angle look. If you have a 200 millimeter lens, you get a little soda straw. And Webb has got a very special optical design that gives it a really large field of view compared to Hubble, but a fairly small field of view relative to Spitzer. And now a comparison of what I'm talking about, that resolution. The image on the left is Spitzer. The image on the right is Webb at the same wavelength. And you can see it's so much clearer, so much more precise. And here's a comparison of Webb and Hubble. Now, whenever you see an image, if it's a Webb image, it's got 6 spiders. It's got that characteristic 6 spikes. Whenever you see a Hubble image, it's got 4. So Hubble has a spider, that secondary mirror for Hubble holds it like that, and so you see 4, and Webb has 3 legs, and that's why you see the 6. So you can always tell the difference. And even in this image, you can see that Webb is more precise, better image than Hubble. Okay, so the science theme number 1, Into the Dark Ages, the first light and reionization. So after the Big Bang, the universe was opaque. Today, the universe is transparent. You can see me because the universe is transparent. And it's transparent because we have atoms. In the early universe, we didn't have atoms. We had just quarks and subatomic particles, and the universe was opaque. And then they came together to form hydrogen atoms. And as those hydrogen atoms came together into stars, the stars formed, and they blew bubbles into the space, and they cleared out the space. So this is the theory that was behind Webb to go forward with in the early days. And when I showed this chart previously, this was sort of theory. And how we study this is, again, we look at the spectra. Is that if the universe is transparent, we can see all these spectral lines just fine. If the universe is opaque, we don't see anything. If the universe is between opaque and spectra and transparent, then we can see the strong lines but not the weak lines. And the other thing is there's this first stars. Those first stars were 100% hydrogen. They were really big. And because they were really big, they didn't last very long. They blew up into supernova. And every time a star blows up, it makes more elements. So a first generation star is 100% hydrogen. The next star has a little bit of helium, maybe some other things. And so every time a star blows up, it makes more and more elements. And our sun is a class G star. And it's a pretty small, pretty normal, nondescript little thing. But that's good. And then, so second generation stars, hydrogen, helium, and a little bit of other stuff. Okay, so June last year, 23, something called the Advanced Deep Extragalactic Survey. They have discovered 1,000 galaxies that existed when the universe was only 600 million years after the Big Bang. Before this image, before this study, they only knew about a few dozen. And the question is that all of these galaxies have very strong spectral lines that are showing lots of star formation. And there's this question, why are we creating so many stars so early in the universe? And why do all these galaxies come together? And that's a question we don't necessarily know. But the spectral lines are showing lots of ionizing radiation, which is helping to clear out the universe. And so here's an example of a spectral line. The vertical line is something called the Lyman break. And by looking, we know where that break is for our sun and what wavelength that is. And I think it's about 90 nanometers. It's way down in the blue. We can't even see it. But where it gets shifted into the wavelengths here tells us, you know, how far away it is. And the bottom, what you can see is this is 2 microns, 3 microns. That's probably 1 micron. So in the visible, our eyes can't even see this. This is in the infrared already. These are the wavelengths that your TV remote works at. So we're finding this stuff is forming much more rapidly than we ever expected. Then this spectra of reionization, by looking at the bubbles, there's no pretty picture here, but they're starting to find that that theory about the bubbles, the galaxy inside of a bubble, they're saying think about a pea inside of a hot air balloon, you know, that like floats over Albuquerque, the balloon festival. They're starting to clear out the universe. And somewhere in this image, where I have no idea, the article, the press release said was a black hole about 10 times bigger than our sun. Oh, actually, there it is. That's a quasar, yeah. And again, that's a single object, and if you look really close, you can see there's the 6 spikes. So anything that has no 6 spikes is a single point object. Anything that's not is like a galaxy. The oldest star, there's a star 6-spiked, and it's a class B star, and about 1 billion years after the Big Bang. And they were able to see the star using a gravitational lens, but generally speaking, I'm not going to try and explain gravitational lenses. This little red dot over there, again, 430 million years after the Big Bang. One of the youngest galaxies. And I gotta say, this press release was March of 24, and every few weeks they come out with, we found something younger, we found something younger, we found something younger, and this is probably the most recent. And it's a galaxy, and the spectra coming from that galaxy says that almost all of its stars are first and second generation. We're only seeing hydrogen and helium in the spectra, nothing else. And it has a supermassive black hole at its core. So this is a prototype, a protocluster. So what this is, each one of those boxes, inside of each one of those boxes is a little red dot. I don't know if you can see it, but those are a bunch of gravitationally connected galaxies. They're gravitationally connected by dark matter. And they're slowly moving towards each other, 2 million miles per hour. 2 million miles per hour moving towards each other. And they will eventually all come together and merge. And I like the analogy to think about it as those are like little leaves, droplets. Those galaxies are like little leaves in a river of dark matter being flowed together. So assembly of galaxies, there's this thing called the Hubble sequence. We have elliptical galaxies, which is on the left. We have spiral galaxies, which is on the right. How do they form? And this is some Hubble data in early universe, and the galaxies are all kind of messy and crazy. But recently, like 30 minutes ago, there were some sirens going through Lakeside, that you might have heard. And you all know that when a siren's coming close to you or a race car is coming close to you and it goes past you, the frequency. So a race car has a higher frequency, and when it goes past, the Doppler effect. Well, the same thing is over here, is that when we measure a spinning galaxy, is that the part of the galaxy that is moving away from us, that light is Doppler effect shifted into the red. The part of the galaxy that's moving towards us, its Doppler shifted into the blue. And so we can measure with different wavelengths, again, and we can see actually these things spinning in the ancient universe. And so here from 22 is some web data at different wavelengths, and each part of this galaxy has a different color, which says that we're now seeing how it spins. From January of 23, another study, an early release, is that there's 11 to 13 billion years ago, we're finding that the galaxies were fairly well formed. There's spiral. You can see there's spiral structure here, and there's some structure there. And it's very interesting is that the ratio of the types of galaxies in this early universe at 11 to 12 billion years ago are about the same as they are in our universe today, spirals and ellipticals, and that kind of. But then and how do things come together? So here's a merging. Remember we were talking about those clusters coming and flowing together. Here's an example. This is a Hubble data of two galaxies merging, and this is what it looked like in the Spitzer. Now this is what the Webb can see, is that we can actually see that there is an extremely hot object that is pulling these galaxies together, and it's not even in either of the two galaxies. So there's something really big out there bringing stuff together. So this is from February of 23. And then this is some more galaxies from June of 23, talking about how they're kind of, as they merge together a billion years after the Big Bang. And this one is, they're saying 50 to 80% of the galaxies that they're finding at 600 million years after the Big Bang are kind of these flattened out structures, which means they're already spinning. They're already spinning, which is flattening them out. This is from January of 24. Also from January 24, comparison of what modern galaxies, just pretty pictures, so ancient and modern. And all of these voids inside of these spiral arms were caused by exploding stars. The stars explode and they clear it out. And the galaxies with the pink and blue spikes in the middle, they've got black holes in their center. So like this, the one here in the center in upper left, those are where the black holes are that cause them to spiral around. Okay, so let's talk about supernovae. Carl Sagan said that we are all made of stardust, and everything that is in our body was created in a supernova. And so when the hydrogen blows up, it produces helium and dust and other stuff. And so you can see that. So here is an early release of a star getting ready to explode. And you may have heard in the news there's going to be a supernova coming up sometime this summer that should be visible from Earth. This one is about 30 times more massive than our sun. And remember, the supernova that blow up are all stars that are really big. Our sun is not going to blow up into a supernova. So we don't have to worry about that. It will eventually turn into a red giant and consume the Earth in about 4 billion years, but we got time. And then, so Cassiopeia A is, I think it's the center of down towards the center of our galaxy. And it was a supernova that blew up about 340 years ago. It was visible from the Earth. And they're starting to do spectra. So the orange and red pictures is warm dust. The peak filaments are clumps of oxygen and argon and neon. Again, we know that from their spectra. We're looking at the spectra. And where does the dust come from to make planets like ours, which we call rocky planets? And so this is an image of a supernova that blew up, and it's got 5,000 times more dust. It produced 5,000 times more dust than the size of our Earth. And when we talk dust, we're primarily talking about beach sand. So think about beach sand is the most prominent thing that gets made in the universe with these explosions. Here's just another real pretty picture, is that as the exploding force field moves out through those layers of material, it's producing what I call a pearl necklace. And the hot spots, it's the shock wave hitting the matter. And at the center of this pearl necklace, that little red dot is a neutron star. So after the supernova blew up, what was left collapsed down and formed a neutron star. And here's a kilonova. And so what we have is we have up in space, we have a Fermi telescope that measures gamma rays. And so when the Fermi telescope gets a big hit of gamma rays, it tries to figure out where it is. And then it tells every telescope in the sky and every telescope in the ground, go look here, go look here. And so Webb went over there and looked, and what we found is a kilonova that had blown up, and we did some spectra, and we found an element called beryllium. I don't know what beryllium is, but it's a heavy metal, so it's a pretty, it's a pretty heavy object to get blown up. Some more pretty pictures from the Crab Nebula. The smoke, the little white smoke, are electrons moving around the magnetic field lines at nearly the speed of light. And as there's something called synchrotron radiation that happens in nuclear reactors. Cherenkov radiation is that when electrons are moving really fast and they change direction, they give off light. And so that's what we're seeing here. And now this is June of 24. This one's just 2 weeks old. Data is that every one of those circles is a star that has appeared over the course of 1 year. So we've taken data, we've looked at this patch of sky, and over the course of 1 year, those stars have appeared. 10 times more supernova appeared in the early universe than ever before known. And in this one little picture, which is the size of a grain of rice, if you hold it out at the end of your finger, that's how much. There's 80 supernovae in that picture. Black holes, so I showed this data last year. This is Hubble Deep Field. There's 47 galaxies that are really old in that deep field, each of those blue dots. Each one of those blue dots has a black hole at the middle of it that was measured by the Chandra telescope. And so the question is, what comes first, the chicken or the egg? Do black holes somehow, does matter come together to form a galaxy, and then as it comes more and more together, that the matter condenses into a black hole? Or is somehow a black hole formed that pulls matter around it to create the galaxy? And here's one example, is that here's a star that was 25 times the size of our sun that blew up. But it didn't produce a supernova, it just disappeared, which means it collapsed directly into a black hole. So again, coming back to, here's the oldest black hole. I don't know where it is in the picture, but 570 years after the Big Bang, July of last year. But coming back to this June, this 2-week-old image, it's also disappears, stars, is that inside of this data set, they're looking at stars that not only appear over the course of 1 year, but also disappear over the course of 1 year. And so those stars that are disappearing, I think, are probably turning into black holes. So science theme number 3, birth of stars and protoplanetary systems. So again, here's our Eagle Nebulae. It's a star-forming region that we can see in the infrared. And it will compare Hubble and Webb data. These are great images. And so the Webb is, these little red things in Webb are previously are stars that are being born. And I showed this last year. So Spitzer, this is the pillars of creation. There are that little piece right there. And with Spitzer, each one of these little green squares is a star. And those stars, the solar wind from those stars is blowing against this red cloud of dust. It's compressing this red cloud of dust such that on the right, you can see where these stars are being formed and born. by the compression of the dust. And here's another image of this star on the right producing a wind that's going a shock wave into dust and compressing it, making it really hot. And then this is some Herschel, data from Herschel that basically shows a star clearing out a pocket, a bubble in a nebulae. So now we get into some web data. July of 23 last year is that this is a cloud complex about 390 light years away. Inside of this image, there are 50 young stars being born. Some of them actually even have planetary disks. The darker regions in the image is mostly dust. And what they want to start talking about is that you can see there's red jets over here on the right-hand side, and there's red jet there. There's several red jets, and they say those red jets are being shooting out of the stars. And we'll show some more images shortly. And I like the, those red jets are molecular hydrogen. And I like this quote about this, sort of like a newborn stretching out her arms or crying into the world just to announce their birth. This is the Small Magellanic Cloud is a dwarf galaxy that is outside of our own galaxies that will someday merge with our galaxy. And it's more primeval than our own galaxy, which means it doesn't have a lot of heavy elements. It's mostly made up of first and second and third generation stars. But we're looking at here is that the blue streaks in this image are dusty silicates, i.e. beach sand. And then there's also some hydrocarbons in there. And the red is warm beach sand. And this is the center of our Milky Way. And this has about 500,000 stars in that one image. Every one of those dots. And the clusters of protostars, I like the quote from the press release, like a bonfire in the midst of a dark cloud. The light blue cyanide that you can see, the lines, is ionized hydrogen. And the needle-like structures of that ionized hydrogen is the hydrogen is being caught up in the magnetic field lines at the center of our galaxy as they spin around our Sagittarius A black hole. This is another star galaxy, Meissner 82. It's located in the Big Dipper. M82 is a fairly famous, most amateur astronomers will image M82. And there's just a beautiful picture of the center of it forming stars. I don't really see green in the image, but it says that there's green specks, and those green specks are sets up of iron. And I should say, maybe at this time, is that all of these color choices are artificial. Because Webb works in the infrared, it doesn't really actually see visible wavelength colors. The folks at the Space Telescope Institute take the data and then they colorize the data according to some rules that they've set up to try and make it more accessible and understandable. The red patches, again, are hydrogen. So again, they've chosen the idea that hydrogen should be red colors. And also they color code based upon temperature. And the red tendrils that are going up and down out of this image are hydrocarbons. And hydrocarbons are important for life. So again, let's get back to this idea of first generation, second generation, third generation stars. So a first generation star, we said, only has hydrogen. A second generation star has got hydrogen and helium. So you can see the spectral lines, that top line is hydrogen and helium. And then that star, when it blows up, the next star is going to have some carbon and helium in it. And then when that star blows up, it's going to have some iron and calcium. And when that star blows up, it's going to have some sodium and magnesium and then oxygen. So you get down into our G-class star, our sun, Our sun, our G-class star, it's got oxygen and sodium and magnesium and iron and calcium and hydrogen and helium. And why is that important? Is that because those are the elements that are needed for life. And it's also important because if your star doesn't have that, you don't have that. We have those elements. Everything on this planet, all of the elements on this planet came from our sun. Nowhere else. Our sun. And so our sun has all the elements that we need to have life on this planet. That's why we have life on this planet. And then when we look out into the nebulae, there's also creations of biochemicals, formaldehyde, organic molecules, methane, methanol, alcohols. And so when we look in these clouds now with the spectra, with Webb, with the spectra, we can find things like, we're inventorying the ices that we're finding in the clouds, carbonyl sulfide, ammonia, methane, methanol, in this data set right here from January. This is, again, the stars. This star, it's actually two different stars. This is a binary pair of stars, two stars that are orbiting each other, and they're shooting out these jets of supersonic material out of their poles, and you can see them interacting with the dust that's around them. These are very long, very young, brand new stars. They don't even have planetary disks yet, but they will. And think about the formation of a planetary disk and these jets is sort of like water going down the drain. So when you take the plug out of your drain, the water spirals down the drain, and the same thing here is that these stars are formed, they spin, as matter falls into them, they spin faster and faster and faster, and then some of it shoots out of the top and the bottom in these jets. Here's another really nice image of a very young star. It's in there. You can't see it because of all the dust, but it's shooting matter out of its north pole and its south pole. And this will eventually grow into a star about the size of our sun. And these red jets have got hydrogen, carbon monoxide, and dust, sand, silicon monoxide. Again, this data, June 24, this is what now, 6 days old, 7 days old. This image up in the upper left corner is more of those jets from a star shooting out and interacting with dust at supersonic speed. From last year, looking at the spectra, methyl alcohol is being formed inside this cloud, inside of the Orion Nebulae. Pretty pictures. This cloud has got alcohol in it. Acetic acid, which is common vinegar, and ethanol, which is alcohol formaldehyde, and sulfur dioxide. It's a sticky, smelly, rotten egg smell, I think. So I guess space might smell like something, maybe. This is again, June of 20 days ago, some data that was produced. And what they're doing here is that this is a young protoplanetary disk, 1 or 2 million years old. That's a small star, it's 10 times smaller than our sun. But they found 13 different carbon molecules inside of its disk. Again, ethanol, ethane, propylene, methyl radicals. Our sun actually has all kinds of oxygen and water, mostly in our disk. So our sun's disk is mostly oxygen and water and carbon dioxide. So let's talk about planetary and origins of life. So everywhere we look in the universe, we see planetary disks. They're ubiquitous. The planets form in the gaps of the arms. And this data mostly comes from ALMA, which is a radio telescope down in Chile, South America. And so the question is, how do planets form? Do they accrete material? By the accretion model is they collect material, it all comes together. And then there's the gas collapse model where it picks up gas and then moves in. So there's different models. But the important thing is, if we're talking about life type things, is you got to look at where's the water. So we want to know what is the habitable zone. So this is a term that we'll talk about shortly when we get to the next mission. But we want to understand what is the habitable zone. What is required for habitation? And what is required for habitation is liquid water. Remember I talked about the black body, really, really hot things have a really high temperature and cooler. So an M-class star is a cool star at around 3,000 Kelvin. An F-class star is a really hot star. Our sun, our G-class star at 55 Kelvin. And so the cooler the star is, the closer in this region where you have liquid water. The hotter the star is, the further out is the region where you have liquid water. In our solar system, Earth is right in the Goldilocks zone of liquid water. Venus is on the inner edge, so Venus is really almost too hot. Mars is on the outer edge, and so Mars is almost too cold. And so where does the water come from? Remember all of those jets that are coming out of those baby stars. Well, stars are basically fountains as they shoot material out of the top and the bottom. And so this is some Spitzer data. And the spectral lines of this data shows that this star is producing a fountain of water out of the top and out of the bottom. And so it's shooting water out of the top. And when it gets up all the way up there, it starts to collect onto some dust. And so the water vapor condenses down onto the dust, and then it falls back down onto this planetary disk that's spinning around. And then the further away you go from the sun, that star, is the colder it gets. And there's these things called ice lines. And so different things freeze at different temperatures. Water freezes at 0 degrees C, 32 degrees Fahrenheit. Carbon dioxide, dry ice, freezes at a much colder temperature. And so what you get is you get these lines where the material changes. So here's called a slow line, is that at that temperature range right there, something changes from water vapor to water ice. Or a little bit further out, changes from carbon dioxide vapor to carbon dioxide ice. Or a little bit further out, ammonia. Or a little bit further out, methane. And that's why different planets, that's why Jupiter and Saturn have a lot of ammonia in them. And why Neptune has got a lot of methane, is that it's where the stuff that's raining down onto our planetary disk changes from gas into ice. And you look at these things, again, in spectra at different wavelengths. And so here's some data and some wavelengths. We want to get in the visible, can get closer in, and then in the infrared, we go further out. So how do we find exoplanets? And these are some charts that I showed last year. This is called the transit method. When the planet moves between our telescope and its star, it blocks a little bit of the light from the star. And so by looking at how much light gets blocked, we can figure out, we go through some analysis in the process and figure out, how many planets there are and how big they are. And Kepler was the mission that did this, and it found over 1,000 planets and over 4,000 potential planets. And then what Webb has done is gone back and confirmed that there's the transit curve. So that's a transit curve from Webb, and you can see the dip. And then what they did is they did a spectra. And that spectra is pretty flat. There doesn't seem to be any carbon dioxide on that planet or any methane on that planet. And so that planet doesn't appear to have an atmosphere. That planet is pretty close to a red dwarf star. It circles its star every 2 days. And again, remember, stars have solar wind. I don't know if anybody saw the aurora borealis this spring when we had our star had its solar eruption. Well, that solar wind is bringing charged particles, which gets into our atmosphere. This star produces a solar wind, which basically is blowing away any potential atmosphere that planet has because it's too close. Fomalhaut is something that's been studied many, many times by many different telescopes, and Webb has for the first time been able to look at the very middle and see this inner ring before. This dot right here in that outer ring is probably a planet. And now we can see into the inner ring. But even that inner ring is 2 times bigger than our own solar system. And so where do the planets get their water? So this is a study of a young, they've actually did a study of 4 different young sun-like stars that are 2 to 3 billion years old. Our star, our sun is 4 billion years old. And it's sort of, fairly middle-aged, where these young stars are like newborns. And what they're discovering is that there's cold water vapor. Remember, that water vapor shoots up, falls down onto the disk, and then moves in and freezes. And so what they're looking at is the snow line, is that at the edge of the snow line, there's a buildup of water vapor that prevents the ice from coming in. And so you get, it acts like a dam, an ice dam. And that's where the ring of icy particles forms at this boundary of the snow line. No pretty picture, but another study of a planet that's a very hot planet, too close to the sun, really shouldn't have an atmosphere, but it does have water vapor, but we don't know if the water vapor is coming from the star or from the planet. It's probably tidally locked to the sun, so that means it's got a hot side and a cold side. So the cold side could have water. And I also said, our own sun, when in the sunspots and the coronal ejections, we also emit water. So they could be coming from the sun. So TRAPPIST is a very famous star system that was found several years ago by Spitzer. It was a study done by a group of out of the Netherlands, and so because they're from the Netherlands, they named it TRAPPIST after or Belgium, the Trappist beer monks. So this is a planetary system named after a beer company, and they have planets that are about the same size as us, but it's much smaller. So the entire TRAPPIST system sits inside of our Mercury orbit. And this is how they found TRAPPIST. This is again with Spitzer. And this was a transit method. So Webb has taken a look at TRAPPIST-C, which is about the size of Venus. They hoped it would have an atmosphere. We don't find anything. So again, it's pretty much a dead planet, sterile. And one of the things is that these Class M, red dwarf planets, these tiny little cool stars, are the most common in our galaxy, but they're also very unstable. They erupt all the time. They have a lot of radiation, and so really they're not a good place to look for life, because anything that's going to be close to them has probably been sterilized too frequently for life to arise. And but then they also looked at, they're finding water in terrestrial belts. This press release didn't have a pretty picture to use. This press release from November did this experiment. They looked at 15 young massive hot stars, and they wanted to know, what could you find? They found water, carbon monoxide, carbon dioxide, hydrogen cyanide, acetylene, and again, beach sand. So we're going to spectra. So one of the ways we can find out what's in an atmosphere is when the planet moves between us and its sun, the molecules in that atmosphere absorb the light from the star. And by the spectra of that absorbed light, we can figure out what's in the atmosphere. And I guess that chart might have gone earlier, but anyway. So we've looked at a sub-Neptune planet with a water ocean using that method. And it has carbon dioxide, methane, but it doesn't have ammonia, which is an interesting question. They don't know why. And so this type of planet is called a Hycean planet. It's probably got a carbon dioxide ocean, a methane ocean. This is back in our own solar system, a picture from May of a water volcano on Saturn's moon Enceladus. And we're going to send a mission out there to look at this pretty soon. That tiny moon is about 4% the size of Earth, has an ocean of salt water, and that volcano is spewing out a plume of water that's 20 times bigger than the planet itself. 10,000 kilometers, about from here, from LA to Buenos Aires. Some more pretty pictures. This is some pretty pictures of the auroras on Jupiter and Jupiter's moons. And actually, Jupiter even has a very faint ring that Webb was able to see. This is Jupiter's moon, Europa, and we're going to send a mission to there. It's called the Europa Clipper. We think that it's got a surface of frozen water ice covering an ocean of salt water. And what we're finding, it's interesting, is that we're seeing spectra of CO2 on the surface of this ice. And the CO2 doesn't last very long. So what that's saying is that it's coming up from the water ocean underneath the surface, depositing itself. We're seeing it, and then it evaporates off into the space. This is a more a recent image of the bottom of Jupiter, October 23. And there's been some press releases recently about the structure of the red spot that we're seeing. It's interesting. So with the infrared, we're looking at the higher levels of the atmosphere because the higher levels of the atmosphere are colder. And I did my master's work on this, and the higher levels of the atmosphere are actually made up of ammonia. The red glow at the bottom, there was an article I had in my newsfeed just a day or two ago. They're thinking that possibly that red glow could be related to dark matter falling into Jupiter's magnetic field. But that's just right now just speculation. And then there was a pretty picture of Neptune with its 7 moons and its ring. And Neptune's a little funny. It sits on its side. Its rings are on its side. And there's Uranus, which is fully on its side, and all of its rings. And Uranus has 27 moons. And again, these are all Webb images. All right, so let's talk more about exoplanets, about how do we directly image an exoplanet. Well, you have to block the light from the sun in order to see the exoplanet because the exoplanet is really, really dim. And the description is it's like looking for a firefly blinking on top of the Empire State Building next to a searchlight while you're sitting in Los Angeles. If of course, the Earth was flat, which it isn't. But I was actually a non sequitur. So I was going to a meeting at JPL, and the freeways were all backed up. I landed in LAX, and so I was taking Surface Street, and I stopped at this. I was hungry, so I stopped at this burger joint on the edge of Watts, and so I'm dressed fairly normal, jacket, tie, travel attire. And there was a bunch of gangbangers there with tattoos on they were very friendly and accommodating. They wanted to know if I was lost. But anyway, so I had a nice burger. But the one guy asked me if the Earth was flat, and I told him that he could prove to himself that it isn't. Just go out to the coast and look out and look for Catalina Island, and then go climb up to a building and look again, and you'll see more of the island. And that's because I don't know if he did it or not, but. So anyway, the way we do have to block the starlight is something called a coronagraph. And this is what we're looking at for the next mission. And so the light from the star comes in, and that's a focus. And then we put a little mask in there, and we block it, the starlight. And then this cleans it up a little bit. And then we bring in the light from the planet. Well, the light from the planet is about 1 trillion times dimmer. And so when we crank up the exposure, we still can't really see it because of errors. So we have to do this deformable mirror to create something called a dark hole. Digs a dark hole. And as the dark hole gets dug, then we can start to see the planet. So that's what a coronagraph does. And there's another planet. All right, and then what we do is we have to look at around the star 2 or 3 times, because if it's back to us, we can't see it. And then we have to see it move in order to say that it's actually something that's orbiting it. So we have to look at it 2 or 3 times. And so here's some data that's from Hubble of a star system. Oh, actually, I guess this is Keck data. It says Keck data. I actually helped make the Keck in a prior, way last century, in a prior life. But these planets are all, much bigger than Jupiter, much further away from their star. The nearest planet has a 45-year orbit. So here's some web data. The star is the little star on the picture, and what we're seeing is a planet in different colors with different science instruments, again with different spectra. This planet's about 12 times bigger than Jupiter, about 20 times further away from its star than Jupiter. So the National Academy of Sciences, so every 10 years, NASA asks the National Academy of Science, what's the most important thing we should do for the next 10 years? And so they said that the next 30 years, really, next 20 or 30 years, most important thing we need to do is to build a mission to go look for exoplanets. Maybe try to find 25 exo-Earths, Earth-like planets around sun-like stars. And so that it'll profoundly change the way human beings view our place in the universe, and it's something that the United States is uniquely qualified to do as the world's leading spacefaring nation. And I should say, the astrophysics division budget at NASA is about $5 billion a year, maybe 6, 5, somewhere around that. The astrophysics division budget and the entire NASA budget is somewhere between 20 and 25 billion. It's not that much. My center, NASA Marshall, is located on Redstone Arsenal, which is an Army base, and Redstone Arsenal in Alabama per year gets about 30 billion. So that one Army base gets more money per year than all of NASA. And NASA Astrophysics Division, $5 billion budget per year is bigger than the space budgets of all of the other spacefaring countries in the world put together. So we're uniquely qualified to do this. And so on, we've just started this. This is the thing I'm working on now. I've been working on this since like November, December, and we're about ready to stand up a project office that'll start October 1st. So we're currently engaged in something called exploratory analytical cases. And that for Webb, back in early 1990s, the NASA straw man for what Webb would look like is this thing on the left. And then we funded a study with TRW and a study with Lockheed, and those were their concepts in the early, we started those studies in 1996 and into those studies at about 2004. And so about 2004, this one over here is what Webb was sort of looking like. And the one on the right is pretty close to what we flew. So you can see the evolution of ideas. There's a book I read about a year ago. It's called How Big Things Get Done. If you're ever into this, I think I mentioned it last year in my talk, but basically the idea is that it takes 6, 7 iterations before you get something right. You have to do it over and over and over and over again. And the first time you do something, in the next iteration, you're going to change 80%. And then the next iteration, you're going to change. And when you're getting down to only changing a fraction of a percent, then you're pretty close to the right thing. So this is what we're looking at for this next big mission, is that there's the EAC case number 1, looks a little bit like a Webb telescope, but actually I'll say EAC 3 looks sort of like a Webb telescope, on axis, segmented. EAC 1 also looks a little bit like a Webb telescope, but it's off axis. And then EAC 2 is an off axis, but it's got a different segmentation. It's got a rigid barrel. And we're designing these telescopes based upon rockets. So EAC 1 is assuming that we're going to put it into a New Glenn or Starship standard rocket. EAC 2 and EAC 3 are for bigger, like the Starship rocket, which is the heavy lift, or potentially NASA's new heavy lift rockets. And so in each of these rockets can put up different amount of mass. And these are what the mirrors kind of look like, which is where this is my primary area, is designing the mirrors, designing the telescope, and working on this. So this is what we're looking at for the concepts. And of course, what we eventually fly is not going to look like any of these. It'll change. So what do we want to do with these is we want to go look for habitable planets. How do we define what is a habitable planet? It's a planet with an atmosphere. It's a planet with an interior. It's a planet with a surface. It's a planet with a core, with a magnetic field. Our planet, we wouldn't be here if our planet didn't have a magnetic field. The magnetic field keeps our atmosphere here. The magnetic field protects us from the radiation from the sun. And then, so how do we look for life? You know, do we look for little green men? No. We want to look for what it is that life does. And what it is, we have, most of you have kids and grandkids. How do you know that they're alive? What is it that they do? They basically eat and poop. So we need to look for the poop. Every single living organism on this planet uses one of these chemical reactions in order to produce energy. And those chemical reactions have byproducts: ammonia, water, ozone, hydrogen sulfide, methane. And so we look for those spectra, the spectra of those chemicals in the atmospheres, to determine whether or not there might be life on those planets. And the other thing is that, so each of those things have spectra. So for this next mission, we're going to look for the spectra of water, oxygen, and ozone. And if we could find methane, that would be the holy grail of looking, or the smoking gun. Those are the primary things we want to look for. I was thinking there should be another. I took a chart out that I should have put back in. The other thing is that our own planet has different ratios and abundances of these elements as a function of its age. Is that before we had blue-green algae, we didn't have oxygen. And so you can look at the evolution of life on a planet based upon the ratio of these different elements. Okay, so Webb's going to see further away than any previous telescope. Actually, I should say, Webb is seeing further away than any previous telescope ever before did. And here is the movie that came out yesterday, 2.2 minutes, about 2.5 minutes. It's a 3D animation of a fly-through, the pillars of creation, merging Webb data and Hubble data. Apparently, there's a longer version of this with some sort of voiceover or music or something, but I downloaded the short one. Again, that's a region of star formation there. You can see the whiskers, the whiskers coming off of the clouds along magnetic field lines. It looks like a couple of jets. So it looks like a single star, but it's out of focus. That star's, you can download it if you want. So that's my story. Any questions? Like I said, that's sort of everything that's happened in the last year. And I'll explain it a little bit further. So Webb is taking data about 10 times faster than Hubble. Hubble at 2.5 meters is in low Earth orbit, and so it can only take data half the time. It can only take data when it's dark. And because it's only 2.5 meters, its collecting area is only about 4 or 5 meters. Webb's collecting area is 25 meters. Webb's collecting area is 5 times bigger than Hubble. That means it collects 5 times more photons. It can take 5 times more pictures. And because it's so far away, it takes data all the time. So it can take 10 times more. It can take in 1 year the same amount of data that Hubble takes 10 years to get. So that's why it's producing so much, yeah.
I was just wondering, do any of the other spacefaring nations have telescopes?
Pardon?
Do any of the other spacefaring nations have telescopes?
Oh yeah, yeah. The Europeans right now have a telescope called Gaia, which is mapping out the stars in space and for looking at space distribution. And it's got a telescope called Euclid that just launched that's going to do mapping out supernovae. And they're planning, Marshall, we actually built an X-ray telescope with the Russians that fly. So all of them fly, and we've also done X-ray telescopes with the Japanese. The Indians have done a couple of CubeSat, small telescopes. Israel has a small telescope, and South Korea is working on one. It's a matter of, I think, national pride to be able to put a telescope in space, and there's a lot of amateur astronomers, you know, that like to build and have telescopes. So, yeah. We're here, and then over there, and then back there. Okay. I'm making John move all over.
Moving about.
Oh no, right here, right this. All right.
Question I have: we're always talking about life on other planets or stars or what have you. We have our own ingredients they have to have.
Yes.
Certain temperature, certain water, certain this and that. Why does other life have to have our ingredients?
Just because we're not smart enough to know about biology that use other ingredients. But so I saw a talk last summer as this thing was starting up. I saw a talk last summer from a lady professor at Louisiana State University, and she's been doing a survey of all the stars that we have in our catalog that have the same chemistry as our star. And there's only a few dozen that are close by that we can look at that have the same chemistry. And my thinking is those are the ones we need to look at first. But I also want to go and say, it's an open question, is that would we have life on this planet if we didn't have a moon? You know, the moon is, I think, essential for to have life on this planet because of the tides, is that the tides and the tidal pools and how that might have impacted the early evolution of life. Would we have life on this planet if we didn't have a Jupiter that was collecting asteroids and keeping us from being bombarded by space rocks? And Jupiter that created the asteroid belt. And this is the other thing, is remember I was talking about how everything falls down onto the planetary disk. The reason that we have iron on this planet is because of Jupiter. Jupiter's gravitational pull kept some iron. We are a relatively iron-poor planet. Mercury, on the other hand, is almost all entirely iron. And there was actually an article in my news feed. I get a daily email of all the stuff I'm supposed to know as a NASA person in case somebody asks me a question. Because I'm considered, quote unquote, a high-ranking NASA official, that means I'm supposed to be able, anyway. There was an article in my newsfeed just recently about the idea that under the surface of Mercury may be a thick layer of diamonds because of the heat and the compression. Anyway, the reason Mercury has all that iron is because the sun pulled all the iron. The gravitational pull of the sun pulled all that iron in to form Mercury. The reason we have any iron at all is because the gravitational pull of Jupiter kept some of the iron from in our orbit to come into our planet. And so you know the old phrase of it takes a village to raise a child? I'm thinking it takes a galaxy to raise a civilization. Is that there are 1 billion G-class sun-like stars in our galaxy. There's probably 1 billion Earth-like planets in our galaxy, but the odds of any of those planets producing us is probably pretty small. Yeah. Anyway, we had a question here and then over there. And then who's next after that? In the back, and the lady in the back. Yeah.
Yeah, first I had the same question as the previous gentleman. But you showed us a video of Pillars of Creation. Mm-hmm. What did that video show you? To me, it was a pretty video.
To me, it's a pretty video.
Well, isn't there some scientific
So,
relevance to doing that and making that video?
So number one, I'm not an astrophysicist. I don't play one on TV. And you're all old enough to get that joke. When I do that at college camp, I can't do that joke in college campuses because they don't know who Marcus Welby is. That doesn't work internationally either. They don't know. So anyway, I build the telescopes. I don't look through them. But I know enough science that I can explain. But they put that movie out just for public relations. So the American Astronomical Society has meetings, a winter meeting and a summer meeting. And there's always a lot of press releases associated with those meetings. That's why there was like 3 press releases in the last 2 weeks, because it's associated with that meeting. They made that video to show at the conference as just a gee whiz kind of thing. Yeah. Okay. And so after you, the guy over here has a question too. Yeah.
Okay, I was just going to ask, how significant is AI in helping you analyze the incredible amount of data?
Yeah, we're looking at that. We're standing that up. We're looking at that. We have initiatives to look at AI. It's going to be essential because the next thing that's launching in 27 called the Roman Space Telescope, which I didn't have any involvement in, is going to produce even more data. Its field of view is 4 times Webb's, and it's going the same place. We are getting to a point where we're producing massive amounts of data. In the past, we've done a lot of I don't want to say amateur community. There's a citizen science. We've offered data sets out there for citizens who are scientifically interested to go through, and they find stuff. But we're now having to train the AI tools because there's just too much data.
Yeah, I saw a program probably about 5, 6 years ago that they said that they discovered a bacteria that lives deep in the earth that thrives in acid, which is completely different from our life form. I mean,
so I know this is what my daughter does. My daughter does microbiology at Johnson, so she would be able to answer that question better than I. I know that they have found bacteria at the sulfur vents at the bottom of the ocean. I know that they have found bacteria in gold mines deep in the crust of the earth. And it's my understanding that every single living entity on this planet has the same DNA. May have different chemistry, but has the same DNA, which then I think one of the most scientifically interesting questions that I can think of is when we go and we do this Europa Clipper, if we fly something through one of those ice volcanoes, can we collect DNA from another planet in our solar system? And does every object, does every planet in our solar system that has DNA have the same DNA? If there's DNA on Mars, is it the same or is it different? If there's DNA on the moons of Jupiter or Saturn, is it the same or different? I find that a very interesting question to ask, and I hope I'm around long enough to hear an answer.
Well, actually, along what you were just saying, if there is DNA in all those different planets, that means it's likely it was seeded from, it might have started on Mars and it got seeded to the next one and the next one and stuff like that. My question is, how is time allotted for the telescope?
Good question. The way it works is that before it launched, a call went out to the scientific community and said, send us our proposals. And so thousands of people sent in proposals of what they would do if they got time on Webb. If I got time on Webb, I go look at this for this reason. I go look at that for that reason, et cetera. They do the same thing for Hubble. And then what they do is they set up a team of people at the Space Telescope Institute and they evaluate the proposals. Now there's an interesting experiment that was done on Hubble, is that they were discovering the analysis of who was getting time on Hubble was mostly famous white men at famous old schools. So they went to a double-blind process where when you submit a proposal, they strip out any information that could reveal your gender, your identity, your school, and now the distribution between men and women, young and old, researchers we see that the awards of time on Hubble is representative of the community of people that are applying. And so there was bias in the system. And we're doing the same thing as we award observing time on Webb. And so they select all the proposals that are going to get time, and then they schedule it so that the telescope moves across the sky in a very efficient manner. And so that we want to look. And so one of the things we discovered very early on is we were getting hit by micrometeoroids kind of regularly. And so we now have to adjust the way we fly the telescope in space to minimize how it gets hit by the micrometeoroids. And so we look at different objects at different times of the year. And then I think we're into the second proposal round, or maybe even the third proposal round. And the principal investigators of each of the major science instruments have guaranteed observing time. And so they get their guaranteed time to go and look at the objects that they want to look at. One of the biggest controversies right now is the idea of exclusion or blackout periods. Is that right now the principal investigators of the instruments have like 1 year to take the data, analyze the data, and publish the data. And we're thinking about, there's a proposal to shorten that time to give them less and less of exclusionary time to make the data available for anybody. There's a big push that data and papers and knowledge that was funded by taxpayer money needs to be available to the taxpayers who want to look at it. No more questions?
Well, thank you very much, Phil.
Yeah.
Thank you. Pardon me? I'm glad you pulled the doors because it was